Recording, recording. Yeah, recording. Good afternoon, everybody. Let us continue with our lectures on linear operators and their representations in Fn. I think I have already introduced these ideas, some of the ideas, but we shall briefly recall some of them so that we'll continue from where we left after the brief recall. Yeah, so what we want to work on is to obtain representations of operators, linear operators on finite dimensional vector spaces as matrices. So let us fix the notation. So X is an n-dimensional linear space over a field F. Now, what we have seen or what we have proved is that X can be made isomorphic to a copy of Fn. Now, the interesting aspect is that it is not just a unique isomorphism that you have, but there are possibly infinitely many isomorphisms that you can define. And this is the real difficulty or disadvantage, or you want to turn it around as an advantage. So by the art of getting this isomorphism is by choosing an ordered basis for the vector space. So let me go back to the figures which I had been drawing earlier. So you have X here, and you have a copy of Fn. Let us get the isomorphism first. Choose any element X here. Now this can be mapped to some element here. And we want a isomorphism phi from X onto Fn such that the linear structures are preserved. Okay. How did we achieve this? Recall that we have chosen an ordered basis B . An ordered basis for X. Then you know that given any X belonging to X, X can be written as some alpha 1 X1 plus alpha n. The unique linear combination of X1, X2, etc., Xn. I mean, this is not merely a basis, but it's an ordered basis, which means the first element, second element, etc., up to the nth element, the positions are fixed. Now, you see that alpha 1, alpha 2, alpha n are uniquely determined. Therefore, I can define a or associate with X a vector alpha 1, alpha 2, etc., alpha n belonging to Fn. And define so for each X, you have an n tuple in identified in Fn, which is uniquely identified. So there is no ambiguity at all. And you can show that phi is an isomorphism. The important thing that we should realize is that the phi is based on the ordered basis that you choose. For instance, suppose you were to permute this ordered basis into some other form, say y1, y2, etc., yn, then you will get a different representation for the same x. That's why I said the isomorphism that you get is not a unique one. There are several isomorphisms possible, and each isomorphism can be generated by choosing an ordered basis for x. This is the art through which you construct this isomorphism. And what you can prove is that every ordered basis for x determines an isomorphism of x onto Fn. Conversely, every isomorphism on x, on every isomorphism from x to onto Fn determines an ordered corresponding ordered basis, which generates this isomorphism. Now, what happens to under this isomorphism? Let us see. See, this is the basic definition that you have used to identify these ordered bases. Now you see that x1 is identified with 1, 0, 0. x2 is identified with 0, 1, 0, etc. xn is identified with 0, 0, 1. Now, this is in our standard notation. This is E1, E2, En. Now, you see that the ordered basis for or the elements, the elements of the ordered basis that you have chosen are mapped onto the standard basis for Fn. Now this is so what you have is this xi, phi of xi is equal to ei. And you can show that, and you already know that a linear transformation on x is completely determined if we prescribe what it does on a base. Okay? Therefore, you see that we have prescribed what this linear transformation phi does on x1, x2, etc., xn. So you can easily now identify what is the image of an arbitrary element x belonging to x into R. So that is what we have done. So you have now, see, x identified with the n tuple alpha 1, alpha 2, alpha n. And it's easy to verify that phi is a linear. If you do this, then you can easily identify that phi is a linear map. Not only that, phi is 1 to 1 and phi is onto. So let me leave it at that. So we'll be coming back. This is the first thing that we did. Now, the second thing that we did is the following. So we worked on what are called linear transformations on X. You know that all linear operators or linear transformation on X are identified, are denoted by Lx. And yeah. And what you can do is the following. Now, let us once again get a picture or a diagram which will explain everything. So you have got a copy of X, another copy of X, and T is a linear transformation from X to X. So the element X gets mapped to the element Tx. Now, let us get an isomorphism of X onto Fn, denoted by phi. So you see that the element X gets mapped to a vector alpha in Fn. Say what alpha is? Alpha is written as alpha 1, or this bracket alpha is alpha n, which is the this is actually phi of. So let us write down this phi. So we apply the same phi here. So Tx gets mapped to an element I think I'll write it as beta. Now, Tx can be written as beta 1 x1 plus beta 2 beta n xn, where x1, x2, etc., xn is the ordered basis B that you have chosen. So this is the unique representation that you have. And beta can be, this can be written as the n tuple beta. Okay. Now, corresponding to alpha in Fn, you have identified a beta in Fn through this linear transformation T. So what do we have? Now we define a map which is designated as bracket of T with respect to. We write B here to identify that this representation is with respect to B, and this is an n by n matrix over F. Which does the following: T B of alpha equal to beta. Well, once again, it is routine to verify that since T is linear, pi is linear, see that is routine to verify that TB is a linear transformation from Fn to Fn. So TB belongs to L, which is uniquely determined. Once you fix D, it is uniquely determined. So it's an element of LFN. And you know that all linear transformations on Fn form a matrix. Okay, so all linear transformation form a n by n matrix. Now this is actually, that's why I said this is an element of M n by n of T of F. Okay. So the representation, so what we have obtained is corresponding to T, once we have fixed the ordered basis, which in turn fixes the isomorphism, you have a n by n matrix identified which maps the image of X to the image of dx. And this is a linear transformation, and it's represented by an n by n matrix. And this we call the representation or a representation of T, or the representation of T with respect to the ordered base, the choice of the ordered base is T. So T is T bracket B is n by n matrix which represents T belonging to Lx in. So what is happening is that X, for X, there is Fn. So it's isomorphic to a copy of Fn. Now, whenever you take a linear transformation on X, there is a linear transformation from Fn to Fn. And that is represented by the n by n matrix, represented by bracket T. I put B also to identify this. Therefore, once you fix B, this representation is uniquely determined. So, by which you also imply that you can get a different n by n matrix representing the same linear transformation if you make a different choice of the basis. Because in the beginning itself, we have said that the choice of the basis for a vector space is not unique. Okay, therefore, corresponding to each ordered basis that you choose, there is a representation for the vectors, and corresponding for each linear transformation on X, there is a corresponding linear transformation on F. Okay, and that is represented by a n by n matrix. And that I think you should work on this. What this matrix representation is. Now we will just find out what exactly is this linear transformation. So you recall that the X is equal to, we have X is equal to alpha 1 x1 plus alpha n. This is the representation. Now, this is identifying X. Similarly, Tx is beta 1 x1 plus beta n. That is Tx. But Tx is also equal to, which is also equal to alpha 1 Tx1 plus alpha 2 Tx2 alpha n Txn. But you know that Tx1, Tx2, Txn are now elements of X, capital X. Therefore, they are linear combinations of x1, x2, etc. Xn. So, in particular, what you have is Txi equal to Txi equal to alpha, or let me put it this way, use A one I, A 2I, A N I, for I equal to, and you know that A I j, there are n square scalars. They are uniquely determined by these equations. It's the important equation. There are n equations here. Now what one does is you just substitute here. So you write beta 1 x1 plus beta 2 x2 plus etc. beta n xn as alpha 1. You just plug in these type of sums here and then get a linear combination of them. And then what you do is, on last time I discussed it, you take the right hand side and the left hand side and then compare, because x1, x2, etc. xn are linearly independent. See that, compare the coefficients of each xi and equate. Okay. Then what you obtain is this, that T P of alpha equal to beta, where you write this one as, and this slight abuse of notation. Actually, it is a transpose, but I write it as column vector. It's actually the transpose of what I have written earlier as alpha. Okay. So if you want, you can just write transpose. And similarly, beta transpose, you write as the column vector beta n. And then you will see that this is essentially TB. Let me write here T transpose. This is equal to by this T, I mean it is the transpose of that, because I have written as a row vector. I'm writing it now as a column vector. if I want to distinguish between them. And then you see that this would turn out to be, if you actually sit down and work explicitly, this would become simply the n by n matrix A ij. That is given by A11, A12, A1n, A21, A22, A2n, AN1, AN2. That is the matrix representation that you get, where these AIJs are obtained like this. Remember one thing, when you write down the matrix for this, what you see is that A1i, A2i, etc., ANI is written as the ith column. Okay. So A1i, A2i, etc., ANI is the ith column that you have for this. So that's how you get the matrix. Okay. So this is the basic equation that you. So we have successfully obtained matrix representation. For example, I just, yeah. You see, suppose you have, I just give an example how to get the matrix representation. And let us take P2R. P2R, which is nothing but the all polynomials yeah, this is defined as theta for P, where P is a polynomial of degree less than or equal to 2. So what you have is Pt equal to P0 plus P1t plus P2 t square. Now you take B as 1t t square. You can show that this forms an ordered basis for Therefore, what you have is the polynomial P in P2R, where all PIs are real numbers, is identified with the triple P0, P1, P2. This is belonging to R3. You know that P2R is a three-dimensional vector space over R, and therefore it is identified with a triple P0, P1, P2. This is how you make the transformation. So once you have chosen this, then this is the. If you choose a different ordered basis, some three polynomials, say 1 minus t, 1 plus t, and 1 plus t square, that also would form an ordered basis. And with respect to that, you will have to rework the coefficients of P, say, and write down get the representation. But now what we want is to how to get the matrix representation. Okay, right. So let us see. All linear transformation on P2R. Suppose T is a linear transformation of that, then let T be defined you know that T is defined or completely defined or completely determined on each vector in P2, provided if you prescribe what it does on the elements of the basis, namely 1t square. So defined by T1 equal to okay, some A one plus A21 T plus A31 T square. T defined by A12 plus A22T plus A32 T square. T square is defined by A13 plus A23T plus A33 T square. Where Aij's are real numbers. So T1 is a vector in P2, which is a linear combination of 1t square. Tt is again a polynomial in P2, which is a linear combination of 1t square, and tt square is given by this. Okay, so that defines a linear transformation. That means the image of each P0, P1T plus P0 plus P1T plus P2T square is now completely determined. See linear. Okay. Therefore, what is going to be the matrix representation for T? Then the matrix representation for T is with respect to the ordered basis B is given by the 3x3 matrix A11, A12, A13, A21, A23. In fact, A11, A21, A31 would become the first column. A12, A22, A32 will become the second column. A13, A23, A33 would become the third column. Now, this is how the matrix representation would emerge. Okay, but that needs to substantiate it. You need some little computation that you have to do. Okay, fine. So that is about the matrix representation. And you see that here, P2R is an abstract or a polynomial space of consisting of polynomials of degree less than or equal to 2, which forms a linear space with respect to the usual addition and scalar multiplication. But yeah, and each vector in that can be identified with a column vector in R3. Similarly, every linear transformation on P2R can be identified by a 3x3 matrix, which acts as a linear transformation on R3. Okay, that is the analog of that. And so that can be easily worked out. So given T, you can work out the corresponding matrix representation. So if you use a different basis, you are going to get a different matrix. This is the problem. So with the choice of each of the ordered bases, you get a different representation for the same linear transformation. So there's a multitude of choice that is available now, which is to some extent an advantage, but certainly it's a sort of something that you would like to, if possible, you would like to develop further. I mean, or rather like to avoid or make a specific choice. I mean, which specific choice you have to make, you should make. This is the point. I mean, there should be some reasonable way in which you want to choose it. There should be some advantages that you gain out of that choice and so on. So let us explore this problem. Okay. So what I want to draw your attention to is the following. Suppose you have two representations. Yeah. So you see that you have two sets now. What do you have? Say X is on F, and this is n-dimensional. X is isomorphic to Fn with respect to certain choice of ordered basis. So what we have resolved is this. Given a linear transformation and an ordered basis, you can compute the corresponding matrix representation. So let's write down. So what have we done? Given T belonging to Lx and an ordered basis B for X, we can compute the matrix representation of T. This is an n by n matrix. Element of with entries for and this is based on the ordered basis that you choose. This representation is based on the choice of an ordered basis. That's all. Therefore, let us write T, the matrix representation, okay, is A uniquely determined. The answer to this is no. That we have seen already. Now the question that you have is the following. Is it possible, this question you understand properly, is it possible to choose an ordered basis for X such that T is represented by an arbitrarily chosen matrix? This is the question. Is it possible to choose an ordered basis for X such that T is represented by an arbitrarily chosen n by n matrix? So let me write this as okay. So what you want to do is this. Be clear about the question. Once T is given and an ordered basis is chosen, you can compute the matrix that represents it. Okay. Suppose T is given and an n by n matrix A is also given. Is it possible to find an ordered basis such that A represents T with respect to that? Okay, so that's the question. Given T belongs to Lx and A belonging to is it possible to find an ordered basis X that T related to that ordered basis is equal to A. Now the answer to this, you don't know at the moment, but we'll make some exploration. Let us consider the identity matrix, the identity operator. Operator I x equal to then I is linear. Now for any choice of ordered basis, I, the representative of I with respect to the ordered basis is given by the identity matrix. That means the matrix which has along the diagonal 1, everywhere else 0. That is where I equal to 1, 1, 1, 0. And therefore, it is clear that if you choose an arbitrary A, which is not equal to the identity n by n matrix, then it cannot represent the identity operator. Okay. So given, so thus any matrix other than I cannot represent the identity operator. Similarly, if you take the 0 operator, the defined by zero of x equal to 0 is represented by matrix. The n by n 0 matrix. That means all entries are 0. It's an n by n matrix with all component or all entries as 0. with respect to any choice of ordered basis. In this case, also the same comment holds, namely that an arbitrary linear transformation A or an arbitrary n by n matrix A cannot be representing the zero linear transformation. Okay. So your question is now completely ruled out. That means given a linear transformation and an n by n matrix A, is it possible to fix a ordered basis such that with respect to that ordered basis, the representative of T is equal to A? The answer to this question is no. So our question is, the answer to our question is this. This is the question that we raised. And so the answer to our question is no. So what have you done so far? We have found that different matrices, in general, different matrices can represent the same linear transformation, except possibly in some cases like this. Okay, right? The art of getting it done is by choosing an appropriate ordered basis. So by choosing different ordered basis, you get different matrices, the same linear transformation. Therefore, the question is that they cannot be arbitrary. See, you see that not every n by n matrix can represent a linear transformation. Okay. Therefore, the n by n matrices which can represent the same linear transformation are possibly related. That's the conclusion. Different matrices that represent the same linear transformation are in some way correct. But how? Let us explore that. Our next task is to explore this. Okay. Okay. So let us return to the old diagram. So let me return to the old diagram. Okay. So the diagram that we have is this. We have a piece of X. belongs to that. Now you have a copy of Fn, a copy of Fn. Now you have a certain isomorphism which is determined by an ordered basis B. So you have X getting mapped to Tx. So this is what you have, phi B, and then this is alpha. This is beta representing Tx, and this that we designate by A. A is an n by n matrix, so A equal to P. Now let me use a different isomer. Okay, so what I want to do is this. I have a copy of Fn, I have another copy of Fn. There is another isomorphism that you have. So you have, say, that is determined by the choice of an ordered basis B prime, and let phi prime correspond to that. This is B prime, phi prime correspond to that. Then let this entity be alpha prime, and this be denoted by beta prime, and this is determined by B, where B is equal to B prime. Okay. Or let me, to be fair, let me set it up. Yeah. Oh. Oh. So let me denote this by A prime. Okay. So how A is related to A prime? Let us work it out. See, what does A do? A maps this representative of X to representative of Tx in a form given by alpha and beta. Okay. So let us do the same thing. So what you do is this. Let me just mark the direction. That would be very interesting to see how it works. Okay. Okay. I go from alpha to X, and then X to alpha prime, and then alpha prime to beta prime. Then I go from beta prime to Tx, and then go to beta. This action is actually carried by A. So let us write it out. Okay. So what do we have? First, what is this action? This action is essentially given by phi inverse. So I just work with phi inverse is the first thing that operates on this. You are here at x, and then from there you work with phi prime. And then you have a prime. So you have reached here. And then you apply what? Phi prime inverse. So this is phi prime inverse. And then you apply phi. This is equal to 8. Okay? This is the relation. Okay? So let me write this. Okay. So A and A prime are not arbitrary. They are related. They are related by what? See that I can write this as the following. Phi prime inverse this is equal to A prime. Now what is this? But you'd see that phi prime inverse is essentially phi prime phi inverse. Okay. Right? Therefore, you see that this is actually, I can rewrite as phi prime phi inverse A phi prime phi inverse is A prime. You see that when you take the inverse, the order changes. Okay. So you see that, what about this? What about phi prime phi inverse? Let us work it out. What is phi prime phi inverse? Okay. So you're first operating with the phi inverse. Okay. But what is phi inverse? You are going from here, Fn to x when you operate with the phi inverse. And then you are applying phi prime. So this is a map from Fn to Fn. It is an isomorphism. It's an isomorphism. Okay. So let me come back to this. And its inverse is also an isomorphism. So this isomorphism, every isomorphism or every linear transformation from Fn to Fn is represented by a matrix. So let C represent phi prime phi inverse. Phi prime phi inverse. So C is an n by n matrix because it's a linear transformation from Fn to S. Okay. Now let me do this. Therefore, you see that A prime is equal to A prime is equal to phi prime, phi inverse, we designate by C, therefore C, A, C inverse. So the two n by n matrices are connected through an invertible matrix C. Okay? Right? So we say that, okay, now let us look at the entire class of now you say that A is related to A prime. This is definition. If there exists an invertible C belonging to such that C A equal to A prime. That's the definition. So we say that A is related to A prime if this is true. So we have seen that given two arbitrarily chosen A and A prime, they may not be related at all. It's possible. Okay, let us come to this point. Now, what type of relation is it? What type of relation is it? You see that this is a, let us explore this. Now you see that you are already familiar with what are called equivalence relations. You see that A is related to A. One. All that you need is choose I as your C. Then A is related to B. Then B is related to A. So if C is the one that relates A and B, then the one that relates B to A is C inverse. Then you have, that is the second property. And the third property is, if A is related to A prime and A prime is related to A double prime, then A is related to A double prime. This is so reflexive, symmetric, and transitive. So the relation is reflexive, symmetric, and transitive. Therefore, it's an equivalence relation. So it's an equivalence relation. So this that's an equivalence relation on Okay. So as what happens usually with the equivalence relation, right? It induces a partition, no? Into equivalence classes. So what you have is you have different classes. Disjoint union of collection of operators, whose union would give you Mn and F. And between two such classes, there is no common element. Or if you take an element from here, from A from here, and B from here, A is not related to B. Okay? A is not related, right? So you have a partition. Therefore, what is happening? You see, what we have done essentially is this. We have induced a change of basis on our vector space. Okay. So each equivalent matrix form is obtained by effecting a change of an ordered basis or choosing a new ordered basis. Okay. So here you see that if you take one block here, which contains all the related, mutually related n by n matrices, then they represent the same linear transformation, and the relation between the linear transformation and this each one of these matrices is that it is a matrix representation with respect to a suitable choice of ordered basis for the vector space. So that's the connection, right? So you see that each n by n matrix in one block will represent the same linear transformation in some ordered basis. Depends on which frame you choose for your vector space to construct the matrix representation. Okay, so it is going from one frame into another frame. That's all. And there is absolutely no and what happens is if you take two blocks, you cannot go from or pick an element from one block and pick another element from another block and go from one to the other through a change of order basis. Okay. So what you see is that every element of a block that you have identified is a legitimate representation of the same linear transformation, or what you call the manifestation of the same linear transformation with respect to some ordered basis. So each representation, okay, and class is a manifestation of the same linear transformation. I usually give the following analogy that the Hindu gods or several forms of each one is a form of the god. I mean, supposedly. Now you see that each one is a manifestation with respect to a certain orientation. See, if you want a god corresponding to what is called Vidya, you go to Saraswati. You want a god or goddess corresponding to Lakshmi or what you call wealth, then you have the manifestation, the corresponding manifestation is Lakshmi, and so on. Okay, so it is something like that. You take two representations which are related to one another. They represent one and the same linear transformation. And that's the interesting thing. Therefore, you see that each block represents the same linear transformation. Okay. Now, the question that you have is this. There's a choice that you have. There are plenty of elements that you can choose from here to represent your linear transformation. Which one you choose? This is our next question. So you should see how the questions are evolving. The questions are self-suggested. Okay. Now we have a choice here to represent a given linear transformation. Which choice you make? Now this is a question that you want to take up. I think I will give you a 10 minutes break and return to this talk. Okay. Thank you. Am I audible?
Yes, sir.
Okay. Fine. So I'll return after 10 minutes and then we'll continue with this question.